Hello and welcome back. We are moving on now to chapter 6 in our OpenStax astronomy textbook, which is titled Astronomical Instruments. And it's basically a chapter about telescopes. So let's learn about some telescopes. We already had a little bit of experience with this. We did a lab on it a couple weeks ago, which you may remember. But let's take some of the things we learned there and add some things and figure out how telescopes work and what they're used for in astronomy. So what do you need to make a telescope? You need a way to bend light. If you can bend light, then you can collect that light and you can make an image out of that light and you can do whatever you want with that light. And there's two basic ways to bend light. One of them is with a lens and the other is with a mirror. So what is a lens? A lens can be made out of pretty much anything but light can pass through. But things like glass, things like plastic, things like water, anything that light enters and can pass through, where the speed of light is different, where it slows down. So we've already talked about the speed of light a lot in this class. It's 300,000 kilometers per second. In a vacuum, it actually turns out that it travels a lot less fast than that in things like glass and plastic and water and diamond and things like that. In fact, 50% slower in some cases. And so that changing of speed, if it comes in and hits this new medium at an angle, can actually physically change the direction that that light is propagating in. And that gives us the opportunity to focus it down into a single point. For instance, if you were to design your glass lens properly and give it exactly the right shape on both sides, then it turns out that light from a particular star, which is all coming in at the same angle, will all get focused down to a single point right here. We call this the focal point of that lens. And if you were to put a little detector here, or even just a sheet, you would see an image of whatever object field you were looking at out here was. Why does that work? Well, because an object of a slightly different location will come in at a slightly different angle, and that will be focused to a slightly different spot down here at the focal plane. And so you end up getting an image of all of the objects that are up here, down here in the focal plane of this particular telescope. Now, you don't put your eyepiece there if this is a telescope. Why? Because your eye is a refracting telescope itself. It uses lenses to bend light and make an image on the back of your retina, in the back of your eyeball. And that retina, those nerve cells in the back of your eye, will convert those signals into electrical pulses, and your brain will interpret that series of electrical pulses as an image, and that's how we see things. But your eyes are expecting that light to come in parallel, just like this telescope is expecting that light to come in parallel. So if you're designing a telescope, what do? You let that light get past focus, and then you put in another smaller eyepiece, another lens down here, which we call an eyepiece, and that will serve to make that light parallel again, so that when it hits your eyes can focus it onto the back of your retina again, and you can actually see whatever you're pointing the telescope at. And so refracting telescopes make use of this bending of light, which is called refraction, which is called why this is called a refracting telescope, to bend the light down to a focus and then finally into your eye. For a reflecting telescope, it works exactly the same, except instead of the primary light gathering element being a lens, it's a mirror. But mirrors can work similarly to how lenses work. If you have a curved mirror with a right surface, then you can, from all of the light that's coming in from a particular direction, focus all of that light onto a particular point up here in the opposite direction, pointing back towards the way it came from. And again, a star that comes in with a slightly different angle will have a slightly different location in the sky, will be focused to a slightly different location on the focal plane, and you will get an image over here exactly the same way as you got an image here for the refracting telescope. Okay, let's take a closer look at both of these designs and think about some ways that that's dealt with. This is a refracting telescope, a picture of a refracting telescope. In fact, this is the largest refracting telescope that was ever built. It is at the Yerkes Observatory, which is in southern Wisconsin, a distant suburb of the city of Chicago. And this particular refracting telescope has an aperture, meaning the primary light gathering element is a lens, and that lens is 40 inches in diameter, right? So that's about 3.5 feet across. A very large piece of glass. In fact, it's the biggest piece of glass that's ever been used to observe the sky with the telescope. And this is an old telescope, right? This telescope was built in 1897. And every single professional telescope that has been built since uses lenses instead of mirrors because of the problem with making really large lenses, right? The problem is that this lens at the top of this telescope is enormously heavy and enormously large. It takes a tremendous amount of glass to design and build a telescope like this. And the problem with this very heavy, massive, heavy piece of glass is that you're having to support it on its sides, on the edges, at its thinnest point. And so there's a limit to how big you can build these things because it will simply crack under its own weight if you build it too big. And in fact, this is why to give it some width on the side, you have to make this thing curved fairly small. You have to make a fairly small curvature here so that you can have a fairly thin lens and still have enough to support it here, and it doesn't weigh an enormous, several tons and only 1 ton. But what that small curvature here means is that there's a small curvature for the light coming through. And if there's a small curvature for the light coming through, that means you have to have a very long tube to follow before that light actually comes to a focus down here near the bottom of the telescope. And so these very large refracting telescopes tend to need enormously long tubes so that the light can finally converge together and then come back on the other side and be focused by this lens or eyepiece at the bottom. And so this is an enormously long telescope for just a 40-inch primary objective lens. And so it was decided at that point that there was no point in trying to make bigger at this point. It was, the dome itself can house a reflecting telescope that's 10 times bigger than this. And so, and the dome is a substantial, sometimes more than half of the cost of the project itself. And so it was decided that there were no more attempts to make a larger refracting telescope after this. And every modern telescope professionally that's been built has been a reflecting telescope instead. Here's an example of a reflecting telescope. This is, I believe, the 5-meter Hale telescope, right? So 5 meters in diameter. That's a huge telescope, right? The 40-inch was about 40 inches is about 1 meter, right? This is about 1 meter in diameter. This is 5 times larger than that. I can't get my hands nearly wide enough to give you a sense of how big that is. But this is 5 times larger in diameter, a mirror, than the largest refracting telescope in the world. And this telescope was built in the early 1900s. Already much, much bigger than the refracting telescopes. But you can see in this picture the basic problem with the reflecting telescopes, right? And that is that the light that comes down is reflected back up in the direction that it came from, right? So how are you going to handle that problem, right? What are you going to do with that light? Well, here's one solution, but let's look at the next slide and we'll see some solutions to the I've sent the light in the wrong direction problem, right? And so here are 3 different options for handling that problem with 3 different reflecting telescopes. Here's one where, okay, all we're going to do is put our detector right at this point. This is called the prime focus telescope, right? We're not going to redirect the light anywhere. We're just going to put whatever instrument it is we want to collect this light with right there, and we'll detect it right where it's at. Another one, and I believe this is called the Newtonian focus because it was invented by Isaac Newton, we know the light's coming back, but before it comes to a focus, let's put a little secondary mirror in here. Here's our primary mirror. Here's a secondary mirror. And this secondary mirror can be a lot smaller than our primary mirror because the beam size will be much smaller here because we're reflecting it back up and we're changing that beam size. And if we time this right, then we can redirect this light out the side of the telescope. And now we can put an eyepiece here, and you can use this telescope by staring in the side of the tube of the telescope itself. There are a lot of, like if you go to buy an amateur telescope off the shelf these days, a lot of them have this design because it's practical and pretty easy to use. And often, especially if you've got a big Dobsonian telescope, right, you might have this at the floor and you're moving this thing around. It might be helpful to have the eyepiece way up here so you can actually see into this telescope at whatever it's pointing at. Most professional telescopes these days use the Cassegrain focus. And here, it's the same principle as the Newtonian focus, except instead of redirecting that light out the side of the telescope, we're redirecting that light through a hole in the primary mirror itself and back down to the bottom of the telescope, which is really a more convenient place to put it. If you've got a big, heavy instrument, for instance, and not just an eyepiece, it's going to be inconvenient just for the weighting of the telescope to put it on the side of the telescope up there. It's much more convenient to have it down here, centered on the telescope itself, and anchored at the bottom of it as it's moving around. This typically isn't a flat mirror; it's typically a curved mirror, and that curved mirror slows down the convergence of that light. And so that it will wait until it gets all the way out the back of this telescope to come to a focus. Now, all three of these designs, you'll lose something. What do you lose? You lose some light, right? There's a mirror here and a physical hole in the primary mirror that's blocking some of the light that's coming in. Same with this. There isn't a hole in the mirror here, but there is a mirror that's right in the direction, right in the way of the incoming light. And so you're going to lose some of that light because it's blocked by this mirror. And even though there isn't a mirror here, you do have to put something. There's going to be some cage or some instrument panel or something that's going to be here, and that will, by necessity, block the rays of the incoming light because it's inside the tube itself. It has to be. And so all three of these solutions to the problem block out some light. Now, is that a problem? Yes, it's a problem. We want as many photons as we can get, but it's not a huge problem. It's just going to make your image look a little bit dimmer, just like putting that central aperture down in lab a couple weeks ago made the image dimmer. You're just losing some of the photons that you had before. You don't get a hole in your image. You're still getting light from all of the objects in the frame. You're just missing some of the light from all of the objects. And so you're missing a little bit of light, which you don't want. But considering the fact that you can make this 5, 10, 15, 20 times larger, losing 10 or 15% of that light you still make up for it in spades in other directions. So this is the way that most modern telescopes are designed these days. Here are some examples of some reflecting telescopes, some mirrors used in actual professional astronomy telescopes. This is the 8-meter mirror of the VLT, which, yes, astronomers were very poor at coming up with creative names for things, stands for the Very Large Telescope. There's nothing more to it than that. And it is very large, so it's an appropriate name. This is an 8-meter diameter mirror, eight times larger in diameter than the Yerkes Observatory telescope. And there's a series of telescopes that have these mirrors owned by the European Space Agency in Chile. And this is a picture of this one after the mirror was just illuminized, so there's no dust on it. It's a beautiful, pristine mirror. But it's difficult to make mirror. It takes months and months to grind a mirror like this down to exactly the right shape. And it has to be exactly the right shape to get the image quality that you want. I'm talking about nanometers in difference over the entire 8-meter square surface of this mirror. And that's difficult to do. And it was realized a couple decades ago, maybe even before that, that it might be easier, instead of making a single monolithic mirror, to make a bunch of segmented mirrors and make a large mirror out of smaller mirror segments. And that's exactly what this is. The Keck telescope. It's a 10-meter diameter mirror, and it's made of, I don't know if you can see how well you can see it on the video, of hexagonal segments. And there's a whole bunch of different, they're all the same size, but they actually have to have different shapes to get the exact shape of what would be a mirror like this to be represented in each of these mirror segments itself. And so it wasn't sure that this would work, but they built it for the 10-meter telescope. And you have to have extremely good control over all these mirror segments, right? If you move the telescope from this part of the sky to this part of the sky, everything bends and flexes, and you have to be able to unbend and unflex all those mirror segments to within a nanometer or two of where it needs to be in order to get the image quality that you want. With modern computers, though, and modern technology, that's a possible thing to do. And most telescopes that are going to be built now that are greater than 8 meters are going to have some sort of design that looks like this. Here you can see the holes in both of these mirrors, because these are going to be used mostly as cast screen focus mirrors. There's a secondary mirror that has to be mounted above both of these telescopes. And so you can actually see the secondary mirrors off of this one, and there's a person standing in the hole in the primary mirror of this particular telescope. But these are some of the biggest telescopes in the world. Okay, so turns out there's 3 ways that a telescope can help you. There are 3 powers of a telescope, and those are the powers of magnification. So telescopes can physically make things look larger. That's light gathering area. Power. Telescopes allow you to gather a lot more light. And finally, angular resolution. Telescopes allow you to resolve 2 objects that are closer and closer together, and still resolve them as separate objects. So here's a question for you. Which of these 3 powers do you think is least important for an astronomer? Obviously, there's no top hat here, but go ahead and write down a guess. What do you think? Magnification, light gathering area, angular resolution. Which do you think is least important to an astronomer? What did you guess? It turns out that the answer is magnification. Most people, when they think, oh, you use a telescope, you're just looking to make things bigger, make it look bigger. That's actually not what we're looking to do. It's the other 2 things that are much more important. We're looking to gather a lot of light, and we're looking to be able to resolve details and things that we couldn't do without a telescope. But the magnification, sure, if you're a pirate on the open seas and you need to know what flag is being flown by a ship in the distance, magnification is important. But for astronomers, magnification, especially without angular resolution, is not that important at all. And in fact, light gathering power is the most important. Angular resolution is a very close second, and magnification is well. It's not that it's unimportant, but it's much less important than the other 2. Okay. So let's talk about light gathering area. Let's talk about light gathering power. The bigger the telescope you have, the more photons you can collect. It's kind of like a bucket collecting rain. The bigger the bucket you get, the more rain you can collect. And if you're interested in studying rain, you want as much of it as you can get. Now, what determines the light gathering power of the telescope? It's determined by the area, right? And so the bigger the telescope, the more surface area that primary light gathering element has, the more light you'll be able to collect. And since the area of a circle goes as pi times the radius squared, or pi times the diameter over 2 quantity squared, that sets the light gathering power of a telescope itself. We never think of like the light gathering power of a single telescope, though, really. What we're talking about, we always think about the light gathering power of a telescope in relationship to another telescope, right? So we're always doing a ratio, and we never have to think about just the light gathering power of a specific telescope. And that makes this formula a lot easier. And so if you're always talking about a ratio, the light gathering power of telescope 1 to telescope 2 must be equal to the ratio of their areas, the area of telescope 1 divided by the area of telescope 2. And that's just pi times d1 over 2 squared divided by pi times d2 over 2 squared. And here's the power of ratios. A lot of these things will go away. The pi's cancel out. The 1 over 2 squareds cancel out because it's in both of these areas. And we don't even need to worry about them. If we're only thinking about how one light gathering power is compared to another, we don't have to worry about the pi's and the 2's. They just go away. They cancel out. And so it's just d1 squared over d2 squared, or if you like, the ratio of the diameters, quantity squared. And so this is, if you're going to calculate light gathering power, it's always going to be with this ratio and this equation in mind. The ratio of light gathering powers is related to the ratio of the diameters, quantity squared. And as we said before, the Czech telescope isn't the biggest telescope in the world, but there aren't that many that are bigger. 10 to 12 meters is about the biggest telescopes that we've got right now. Okay, so let's try. Oh, here's a visual of that rain bucket analogy that I was making a minute ago. Again, if you want to gather rain, you can put a bucket out while it's raining. And the bigger the bucket, the bigger the area, the bigger the aperture of that bucket that it has, the more rain you will collect, right? So here is a large bucket, here's a smaller bucket. And as that rain fills the buckets, you're going to notice that it fills up at the same rate, right? The height after a certain amount of time in this bucket is going to be the same as that bucket, but there's a lot more water in this bucket. Why? Because the mouth is wider and it's been able to, at the same amount of time, collect a lot more of that rain. And so the same thing works with telescopes. The bigger, the better. We want to collect as much light as we can. We want to build as big a bucket as we can, right? Because that astronomical object that we're interested in, those photons are washing over the entire Earth all the time, right? And most of them are being wasted. We're not even detecting them. That telescope will collect a certain amount of those photons, and the bigger the telescope it is, the more of that rain and starlight that you'll collect. Okay, so here's a thought question for you. How does the collecting area of a 10-meter telescope, among the biggest in the world, compare with that of a 2-meter telescope? 2-meter telescopes still way bigger, twice as big, in fact, as that Yerkes telescope, but it would be considered kind of a smallish professional telescope by today's standards. So let's take our little equation out for a spin, shall we? Let me stop this share and begin this share. There we go. Okay, so the light gathering power of telescope 1 divided by the light gathering power of telescope 2 is equal to the diameter of 1 divided by the diameter of 2, quantity squared. Now, what are my two diameters? Well, I know that one of my telescopes is 10 meters and one of my telescopes is 2 meters. When I multiply those two, divide 10 meters by 2 meters, the meters go away. I need to make sure they have the same unit, or that won't happen. So if they don't have the same unit, you're going to have to get them in the same unit. But it's as simple as this, right? This is 10 divided by 2, which is 5, quantity squared, and 5 squared is 25. 5 times 5 is 25. And that is light gathering power of telescope 1, the ratio of that to the light gathering power of telescope 2. What's that mean? It means that a 10-meter telescope is 25 times better than a 2-meter telescope at collecting light. It means that for every 1 photon that 2-meter telescope collects, the 10-meter telescope will collect 25 photons. It's 25 times faster at doing everything than the 2-meter telescope. And so that's a huge deal. That's not just a small factor. That's a big deal. Okay. That is a pretty good stopping point for today. We will come back and think about Friday's class next time, and we'll get on to the other powers of the telescope, specifically the other one that we care about, angular resolution. Okay, see you then.